Hello and welcome back. In the previous video, we talked about the Kalman filter algorithm, and also I shown you that how can we use a linear Kalman filter for a state estimation task. And as you see here, for this case study, I assumed I know the excitation force, I know the acceleration of the vibration, which is x double dot. Assuming we know the mass, damping, and the stiffness of the system, I was able to estimate the displacement and velocity of vibration, assuming having a noisy measurement. Now, the next question I'm going to ask is, in a real case, usually we don't know what is the stiffness of the system. We don't know what is the damping of the system. Assuming we can the scale, the mass, but we don't know the stiffness and damping. How can we solve such a problem using Kalman filter? Or my next question is, can we use Kalman filter to identify any parameter in the system, a dynamical system or not? For example, for the same problem, I assumed I know the excitation Ft, I know the mass, I know the x double dot, but I don't know the c, I don't know the k, I don't know x, I don't know x dot. And as I said in the previous presentation, this is a nonlinear system identification problem because if we don't know the x, k, we don't know the x, then if we k, for example, this x as one of the unknowns, this k is another unknown, then this is a nonlinear system identification problem. Then if we want to solve this using Kalman filter, do you remember for a state estimation problem? For a state estimation problem, I assumed my state vector was x and x dot. For parameter identification problem, the state vector will be x, x dot, k, and c. You see here? Then for this, in this dynamical equation, we have these four unknowns to be estimated and identified. We call this state vector an augmented state vector, and usually we call it joint state parameter estimation system identification problem. Then, for example, if I want to use a linear Kalman filter here to see if we can use Kalman filter here to solve such a problem or not, we have these mx double dot x dot kx equal to Ft. Then we need to convert the equation into a state space form. I assumed I have four states, as you see here, and I wrote here for you x, x dot k, and c. And the A matrix will be something like this. This is the excitation. We have the measurement, assuming we have acceleration as a measurement. And this is my A and C matrix. You see here, we have k and c in my state vector. And in each iteration of the Kalman filter updating process, we have to update the A matrix because we have k and c, which are corrected in each iteration, and we need to substitute these corrected states into the A matrix. You see, this increases the computation. And I implemented the coding. I can put the code in the description for you, the link for the code, and you can have access to. But the thing is, if you look at the estimated states and parameters, you see that the Kalman filter was able to estimate the states and identify the parameters. For example, this is the stiffness value, and this is the damping value. And one point I want to mention here, as I said before, Kalman filter is a Bayesian. It means to start the algorithm, we need to impose the prior knowledge to the algorithm. And for this case, for example, as you see here, for damping, for a stiffness value, I assumed my initial stiffness, as I wrote here. For example, I say K0 is Newton meter. This is my K at time n equal to 0. This is the mean of the prior knowledge. And I need to mention the P0 as well. And for this case, I assume my P is 10 to the power 9, for example. That is the reason at the beginning of the algorithm here, the mean of the initial value is 30,000. But in the first initial iterations, you see such a big jump we have, and after sometimes the filter catch the ground truth and get stable. You see here, and such a thing happens for damping value as well. The reason I use such a big number as initial P, because this initial P let the Kalman filter go and search such a big in a big domain and try to get the best answer to minimize the error of this filtering problem, which I don't want to go into the detail here for you. Okay, then as you see here, this although a linear Kalman filter, based on the theory and assumption we had to develop the Kalman filter, should not be able to estimate the parameters because it's a nonlinear system and integration problem. It was able to do it. But the question I'm going to ask is, what if the system is highly nonlinear? For example, for this case study, as I've shown you here, this was a simple one order degree 1 nonlinear problem, and you could write the equation in a matrix form. But assume you have a DoFing equation. For example, the equation is something like this: is mx double dot cx dot k1x plus k2x to the power 3 equal to ft. In this case, we deal with a highly nonlinear system, and we cannot write the equation in a static space form. Then what should we do for that case to find the matrix A and go and calculate and predict the state and its covariance matrix? The first solution people have been using was Unscented Kalman Filter. Extended Kalman Filter. Extended What is the basic of the extended Kalman filter? The extended Kalman filter works based on the first order linearization of the Taylor series. And it says that your A matrix, for example, let me write it in another way. Then you assume you have X in a discrete domain, or let me write in a continuous domain, you have X dot, which is equal to F of a nonlinear, arbitrary nonlinear function of your state vector, your input, and your noise, and you have your measurement function, which is an arbitrary function h of your states, your excitations, and your measurement noise. This is an arbitrary nonlinear function. Then you cannot write it in a matrix form. For these kind of equations, extended Kalman filter tells you that you can linearize this function and find your matrix A based on the round of your F respect the round of the state vector. And your C matrix, the same way, will be the partial derivative of your H respect your state vector. Using this technique, you can define the A and C matrix. And again, use the linear Kalman filter algorithm we defined earlier. You see here what we are trying to do. We are trying to approximate or linearize or approximate a nonlinear function with a matrix and come back to the linear Kalman filter and work with that. But sometimes we have some kind of function that first order or second order linearization is not enough to get rid of the nonlinearity. Or sometimes we cannot calculate the derivative of the function at all. Then what should we do in that case? Okay. Then to answer to these questions, Unscented Kalman filter has been developed. Unscented Kalman filter look at the Kalman filtering problem from a different point of view. And the way we define the linear Kalman filter in the previous video can help us a lot to look at the Unscented Kalman filter in a simple way and understand the algorithm. Thank you very much. See you in the next video.